change it from radiance to reflectance, and then denoising. And there are different steps for denoising, like uh, that Eigen's formula. We can use the Eigen's formula by squaring. Yeah, 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 yeah.
Today we have learned about the hyperspectral imagery and its difference with multispectral. Then regarding the what are the like how the satellite takes the images. Then about the bed lines, removal of bed lines. Then thereafter regarding the softwares. That
are sitting on this. All right. They are not answering from day one itself. We'll make the progress. You have to shift somewhere in some. क्या वो effect था? This effect. Current जो है ना, current that is generated due to the magnetic effect. Want to break that. What did I do? Circular current.
So audible, right? Mm, this lecture is a little bit harder than the previous lecture. So if you have doubts at any point, absolutely stop me, ask me, because it will take a little bit of time to understand it. So far you have been learning about optical remote sensing, right? So what happens in optical remote sensing? We are looking at band information, and band information is telling you about the color, different colors which humans can see, and then the wavelengths which we can't see also can be treated as color. So apart from this spectral information, we can get information about structure and other properties of the material using microwave remote sensing. So do you remember we saw the electromagnetic spectrum in the beginning? We saw visible light from 400 nanometer to 700 nanometer. Then we saw that after that is infrared, and after that what happens? Even larger wavelengths come, right? So we saw near infrared, short wave infrared was there, then thermal infrared or long wave infrared is there. Do you want me to go back to that slide and show you? Okay. Sorry. So we have violet to blue over here, and then we have red over here at 700 nanometer. Beyond that is called the near infrared, short wave infrared, long wave infrared, and then for the next step we have microwaves and radio waves. Did you all learn about wavelength of light? This is my phone. Yeah. Did you all learn about wavelength of light? Yes? You all are aware. Okay, let me just try to explain from this thing. So all those wavelengths we saw red color, blue color, I was saying 400 nanometers, 700 nanometers, that is the wavelength, okay. So any wave looks like this, right. So if I am going to say this distance to this distance, that is one wave, correct. So this next wave is over here. So one full upper location and one full lower location, okay. So this crest and this trough, it's called, the upper one is called crest and lower one is called trough. So crest and trough together make one wave. the distance from here to here is a wavelength. Okay. Now I am calling this black as A, and there is another one B. Which one has a longer wavelength? B has a longer wavelength. B has larger number of waves in the same location. So if you see, the wavelength is from one crest, one trough. Here it becomes this way. So even though it starts somewhere over here, it ends much before this closes. So the wavelength of this is large. It's a longer wavelength. This is a shorter wavelength. Okay. Now the number of waves that are there in a particular time period, that is called as frequency. So the this number of waves is more for B. A is having lesser number of waves. So we can say this has higher frequency, smaller wavelength. Lower frequency, higher wavelength. Okay? This much is clear to everyone? Fine. Now back to the electromagnetic spectrum. Where did it go? Yeah. Electromagnetic spectrum, we are able to see that blue and violet is having very small wavelength, 0.4 micron or 400 nanometers. Red is somewhere close to 660 to 700, and this near infrared we saw when we were doing NDVI calculations, 800, right? So like that, all of these are longer wavelengths. That means shorter frequency, right? Smaller frequency. Now in case of violet and blue, everything on this side, ultraviolet, X-rays, gamma rays, are having very short wavelength and a high frequency. Okay. So this is just for your understanding. Now how does light interact with matter? That varies from not only the type of matter that we are working with, but also based on the light that is incident. Okay. So we saw in general the sun and the energy that is coming from the sun. Now based on what the energy is going to be, like how the energy is interacting with the matter, there is going to be a different response on that light. We learnt about reflection. That is the case when the wavelength of the light is very small compared to the size of the target. For example, the wavelength of the visible and near infrared light is in the range of how much? In nanometers, right? Nanometers is very, very small, like it's 100 and 1 divided by 10 to the power 6 of a millimeter. So we can't see all of that. So when it's interacting with us, it is just going to be reflecting. But when the size of the material is very, very small, the target is very, very small, then it will not interact in the form of reflection. It will be called scattering. Its path is going to change, and not in the loss of reflection, but in the loss of scattering. So in case of microwave remote sensing, which lies over here, the wavelength is very large. The wavelength is large enough that when you are interacting with the other objects in this room around us, the buildings, the wavelength is comparable in size to that. So we will have to go for scattering, understanding scattering. That's why it's different from what we have learned in reflection. Reflectance will tell us the spectral properties, scattering will tell us the structural properties and some other properties. Let's take a look at what microwave helps us to understand. So I think I'll skip the first 3 slides because this will be unnecessarily scary. Let's just jump right into the microwave. Okay. So I've just the first 3 slides very basically I have explained so far, but then those are essentially how the light is going to be interacting with the surface. Okay. In addition to scattering and reflection, there is one more thing, and that is called emission. So, emission is basically dependent on the temperature of the body. A body at high temperature, I mean all bodies will be emitting some light of their own, and that completely depends upon the temperature. Okay. So, those which are having high temperature will be emitting at a shorter wavelength. Those with a low temperature will be emitting at a higher wavelength. So, based on the temperature of the earth roughly, that based on that we can say that most of the emission of the earth is happening somewhere in wavelength of around 10 micrometer, that is 1000, no, how much is it, 10,000 nanometer. Okay. So, 3 forms of interaction of light with targets we have learned. What are they? Reflection, scattering, emission. Okay. Now, in case of microwave, we saw that the wavelengths are very, very large. It is in the range of 0.1 centimeters to 1 meter. So, then because the wavelength is comparable to the size of the target, it is we will be able to understand how it is the targets are going to scatter the microwave radiation. Okay. So, one advantage of having microwave, so in case of visible light and in case of infrared images, you would have seen that satellite images will be having clouds, right. So, what are these clouds made of? Clouds are made out of small droplets of water and a few other like smaller, very, very small particles. But then when the size of those particles is very similar to the wavelength of the light which we are using for imaging. So, that is why it is getting blocked by that. We are not able to see through that if there is a cloud. But in case of microwave, because the wavelength is so large, it is not going to be affected by these water vapor and other things which are there, and it is very see through to the atmosphere. Okay. So, we are able, you all have learned atmospheric windows? Okay, let us not worry about it. We are able to see through the clouds with microwave data. So, for the northeastern states it is going to be very useful, no, because majority of the period of the year there is always very, very heavy cloud. So, advantage of using microwave is that we can see through these clouds, we can understand, but there is one major disadvantage. It is not as simple to understand what the microwave data is showing us, and especially when there is a lot of changes in the terrain, if there are mountains and hills, then the correction becomes very difficult. Okay. So, that is a disadvantage, but let us just talk about a little bit more about microwave before we jump into the advantages and disadvantages. You all have learnt about passive and active remote sensing? Yes? Okay, tell me, what is it? No, it's okay, I am not going to torture you with that, it's okay. So, if you all happen to know and you all are confident to answer, please feel free to answer, otherwise it's okay. Even if you all don't know and you would like to take a guess, go ahead, I will correct you in case you are wrong. Exactly. Yeah. So, in case of passive sensors, it is like what we had seen earlier. Sun is a source of light, and that source of light leads to light being incident on the target, and the target reflects the light and it goes to the satellite sensor where it is going to be visualizing the data, getting the data. Active sensors have the source of light themselves. Advantage of this is that it will be having, it can work at night time also when sun is not there, right. So, it has day and night capabilities. Okay. So, that is the advantage of having microwave remote sensing in active remote sensing. Microwave remote sensing can be done either in passive mode or in active mode. Passive mode is the instruments are called radiometers, but generally it's got a lot of noise in it, and so much noise that is really difficult to distinguish from the signal. So, generally this is not, I mean, while it has its own uses, the spatial resolution is very, very large. Okay. So, spatial resolution is large, so that we will be able to maximize on the signal and minimize on the noise. So, that is how it is for passive microwave remote sensing. Active microwave remote sensing are those which are having their own source of microwave, I mean of the microwaves which are sent towards the surface, and then that is going to be scattered back, and the sensor itself is going to detect it again. So, that is called active remote sensing, and this can be done in two ways. One is non-imaging. So, in case of hyperspectral also we saw non-imaging and imaging. What happened there? Non-imaging was spectroradiometer, only one point. So, point based measurements. But in case of imaging spectroradiometers, every single pixel is going to be having the information that that point based one is giving you, right. So, exactly the same way there are non-imaging sensors called altimeters and scatterometers, and then there are imaging sensors, which is going to be the focus of today's lecture, which are radar based. So, radar you all might have heard of it being used. You have heard the word radar, right. So, it is radio, anyone? Detection and ranging. So, radar is again of two types, side looking aperture radar and synthetic aperture radar. We will talk about all of this in the subsequent slides. Okay. So, like how we have different bands in multispectral and hyperspectral, like that in case of microwave also we have different bands. So, we saw bands refer to different wavelengths, right. So, different wavelengths of the common microwave bands are mentioned here. Now, because microwave was used by this army and military in the past, so then they had these code words for them instead of directly referring to them as just band 1, band 2, band 3, that will become too simple, right. So, then they had these code words, so they used to refer to them as K band, X band, C band, S band, L band, P band. Then because K band can be further split up, we call it K above and K under. Okay. So, this is the range of each of those, the associated wavelengths. Now, like how we said every wavelength, we saw that we drew the waves earlier, and then we said that there is some different light has different wavelengths and different frequencies. If it is a low wavelength, I mean very small wavelength, it is high frequency, right. So, accordingly you can see that also over here. This is high wavelength in centimeters, 30 to 100 centimeters wavelength. The frequency is 0.3 to 1 gigahertz. Okay, gigahertz means into like 10 to the power, how much is it? 10 to the power 6, I think 6, right? No, 10 to the power 9, 10 to the power 9 per second. Okay, so that is the measure of frequency. So, yeah, so each of these bands have their own unique set of applications. So, you can note down from here, or you can take access to the slides, that will be fine. So, generally we will see why each of this is happening. We will come back to this slide, but generally the longer the wavelengths, the more it can go into understanding the structure. For example, if you have a forest and then you are looking from a small, like our optical thing, then we see what is happening at the top of the forest. With microwave, you can go a little bit into the interiors of that canopy, the upper part of the leaf structures, all of that can be seen. Then if you go for these bands, then you can go even up to the interior structures, the branching structures and the trunk and the complete biomass related studies can be carried out. Okay. So, these are some examples of the microwave satellites. Indian satellites are the first two series, RISat they are referred to. So, they are in C band and X band. Where does C band and X band come here? In this range. Okay. 3.8 to 7.5 is C band and X band is 2.4 to 3.8. Alright. Now apart from that we have some other sensors. This sensor data is free. Sentinel-1 you might have heard of, that is freely available for all to use. In addition to that we have one upcoming mission called NISAR, which is a NASA ISRO SAR. SAR is synthetic aperture radar. We will talk about that in the next few slides. So that has L band and S band. So that is 15 to 30 and 7.5 to 15. Okay. So what is it going to be used for? It can be used for vegetation mapping, biomass. Then it can also get the soil moisture because it can penetrate the entire canopy structure and go down, right? So then we can see the soil moisture. And then in S band we can do standard agriculture monitoring and other things is done in S band. Okay. So this is how a radar is functioning. It's radio detection and ranging, the full form. You have, I'm just talking with example of a simple radar, okay. So we talked about active remote sensing is going to have source and detector in the same platform. Otherwise for passive, source is something else, maybe the sun, and the detector is on the sensor. Correct. So here we have a radar which is active, and we have first in red the source of energy which is going out, and then this is going to be back scattering it. So that is going to be returning it, and that is going to be detected by the receiver. So transmitter transmits, it is scattered back, and then it is received by the receiver. Alright, clear so far? Yeah? Okay? Doubts? Yeah. Okay, I will explain this part again, or previous ones also, the different wavelengths and everything. This one, okay, fine. So think of it this way. You understood for optical, like for hyperspectral, multispectral. So what happens? Let's take the example of our eyes. White light coming from there, hitting the surface, and then it's coming back to us. I mean, it's coming everywhere, and a part of it is coming to us. Our eyes are able to detect it. This is called reflection. Suppose, like in this case, our eyes are only receiving the light. It is not giving any light of its own. Suppose we did not, suppose we were in a dark room, there is no light at all. Then we had to see something. So we can attach, if we are attaching like a small torch or something. So then we itself are giving the light and we are detecting the light, the reflected light. That becomes an active sensor. Okay. So in case of radar, it's like that. You're having a transmitter which is transmitting the lights, and then that is going to be returned by the target, and that is going to be received by the same. Okay. Sending and receiving by the same thing, and this is the target. So over here I am just talking about a simple radar example. In case of airports they are using this, but otherwise if you are placing them on a satellite, we will be getting from the surface. The satellite is going to be sending it towards the surface will scatter it backwards, and then we will be able to receive back at the satellite. Now you all are aware of this speed and speed, distance and time relationship. Yes, speed is distance divided by time, right? So if you are having a measure of when you have sent the signal and when you have received the signal, right? So you have sent, assuming that you have sent the signal you have sent the signal at time t1 for send, and t2 you have received. and target distance is L, but we don't know L. Sorry. Okay, target distance L we don't know. So what happens here? We have sent at T1, received at T2. So the signal has gone L, come back L in the time T2 minus T1, correct? Yeah, I have sent at 1 o'clock, I have received at 1 minute afterwards I am receiving it. So then 1 minus 1 o'clock will be 1 minute, that time period, right? So that is T2 minus T1 we have got, and by that time the signal has gone, hit the target and come back. So it has travelled a distance of 2L. So the distance is 2L, the time is T2 minus T1, that is going to be giving you the speed, and the speed is the speed of light. The speed of light is going to be a constant, right? What is it, 3 into 10 to the power? Yeah, 3 into 10 to the power 8, right? So now we have the speed of light over here, and then we know the time distance, the T1 and T2 is known. From that we can calculate L, correct? Yeah. So that is how we are estimating the distance from a radar. So I just want to come back over here and tell you all about this non-imaging sensor altimeter. I didn't explain it before because I wanted to explain this concept before we came back to it. The non-imaging sensor altimeter is doing exactly this. It is sending a pulse of light and it is receiving it back, and then it measures the time between the send and the receive. From that we can get the distance very accurately. Okay. So this is a non-imaging sensor because it just sends at one point, then when the satellite moves again or whatever, it sends again and then again and again. So we will be getting at multiple locations both the distance to every single point. So this is called an altimeter. Now we will talk about scatterometers a little bit later. Now yeah. So this is this slide talks about the advantages and disadvantages of using radar. Now the first advantage is that because we have our own source of light, we are the ones sending the signal and receiving the signal anyway we are doing it. So because of that we can operate at any time. Day or night does not matter. We don't have to be dependent upon a source of light for this, right? So day night operation is feasible, and that is one major advantage. And then the second one is that it does not matter whether there is rainfall or no. So the transmission of the wave of the microwave for how much rainfall is there, that is what is shown over here. So for a light drizzle we are able to have like lower frequencies are going to get very like they are going to get attenuated. Sorry, I am using a tough word, right? Yeah, so this is a transmission, by the way, huh? So transmission is going to be from 0 to 100. 100% transmitted means all the microwaves are allowed to pass. 0% transmitted means that they are not allowed to pass through the atmosphere. So in case of near infrared or visible, when we saw a cloud, then how much is the transmission? 0, right? Because it is not passing, we are not able to see the surface, no? We are not able to see the surface, we are not able to receive signal from the surface. So that is why it is 0% transmission. But in case of microwave, as we are going for wider frequencies, we are able, the transmission is going towards 100, okay? Sorry, not frequency over here, sorry. If you are going for larger wavelengths, the frequency is going towards 100. lower frequencies, okay, lower frequencies, larger wavelengths. Larger wavelengths, transmission is close to 100, and even in case of, this is heavy rain and this is light drizzle. This upper layer is light drizzle. So for wavelengths of which bands are there? Do you remember over here? K band is around 1.1 to 1.7. P band is 30 to 100. So let's see how that goes. So 30 to 100 is not there in the scale. Let's find something around 9. So C band or S band. So C band will be somewhere over here, S band will be somewhere over here. So in case of heavy rain, it will be still giving around 90% of the data is still going to be transmitted, and in case of S band, even more than that is going to be transmitted. But if you are going to go for the initial bands of K band, then what happens? It's around 1, right? So only 10% of the data is going to be transmitted. So for heavy rainfall, maybe K band is not suitable, but for a heavy rainfall, if we have say C band or S band or higher bands, then we can use it very easily. So another advantage is that for those higher wavelength radars, we can even image the surface when it is raining or when there is a lot of cloud cover. This is advantageous, one, because this area particularly is always having cloud cover, almost always having cloud cover. Secondly, in case of disasters like floods and landslides, it's all because of rainfall, right? And if we are not able to see the surface during this period, then it's not really going to help us understand or provide any useful information to the users. So having this is going, we will be able to see what is happening on the surface, on the ground, and provide what support needs to be done. Clear? It's fine? Now, the problems associated with microwave is that we are not getting information about the composition of the material. Like how in case of spectral or hyperspectral, we were getting all the absorptions and the peaks and everything. So from that we can identify this is definitely this material, this is definitely this material. That we cannot do from microwave. We get structural information, we can get, you know, roughly this is a hilly area, this is a flat area, there appears to be some formation over here. So in case of landslide or something, definitely feasible. But if you want to, you know, go for within the crop, any sort of stresses, the water stresses that might be there, all of that is having some limitations when it comes to that. Okay. Then second thing is the sensors are very, very complex and expensive to set up. So for a smaller user, like a small government department, it might be expensive to procure their own UAV sensor. Even the data sets which is coming from satellites, that is very expensive. Except for the few free sources that we mentioned, most of them are a little expensive. So it becomes a little bit difficult for us to acquire. Okay. So those are the disadvantages. So just to show you a few examples, just to show you a few examples. This is an example, an image, a regular multispectral image of a volcanic explosion. What do you see over here? Complete smoke and everything, right? See here, from here the smoke is all not appearing. It looks perfectly okay. So this is a microwave data of that location. Now, this area, completely cloudy. How does it look like over here in the microwave? You can make sense of it. You can see there's a braided river channel over here. All of those details can be seen, right? So these are some of the advantages that microwave remote sensing will be giving you. Don't be scared looking at this equation. It's a very simple equation. This is talking to us about the power which is received by the microwave sensor, right? So microwave sensor is going to be transmitting some energy, that is in the form of some, that we are calling it as some power transmitted, and then we are going to receive the energy, that is the power received. So power received is what we are measuring, correct? power received is what we measure. Don't worry about the equation at all. I am just going to explain it to you from intuition. Power received depends upon how much power we send to the surface, correct? And then the energy over, I mean the surface area over which we are getting the signal, right? And finally, it is also dependent upon the target, how much it is scattering back, whether it is being scattering back towards the sensor or no. So, those are the major factors which are affecting this power received at the satellite sensor. Okay. So, let us see, how do I explain this? So, this first, I think we can skip this also, because this first term is essentially telling you about how much is the transmitted power per unit area. So, that is why this 1 per unit area 1 by 4 pi r square is coming there, and then this is the power which is sent towards the surface, the power of the antenna plus some amplification factor which is added to it, that is the gain. So, you multiply that and you send it towards the surface, and the second one is how the surface is sending it back towards us. So, that is mentioned over here, and finally, this is area of the receiving, how much area is used for receiving it back, and that is mentioned over here. So, totally we get a power received equation here. Do not need to by heart it, do not worry at all, it is never going to be asked in the exam about what is the power received or anything of that sort. Just need to understand that it depends upon the 3 factors: how much power is sent from the top, how much is being sent back over here, and how much area we are trying to detect totally from back at the receiver. Okay. Now, some more scary equations. Yeah. So, yeah, really, no one is going to ask you these things. Absolutely don't panic. I am just going to try to explain to you. Yeah, I will just try to explain to you how the data that we are getting, you might hear from people that the data has a real component and an imaginary component. That might be some people who are working in microwave will be telling you about this. So, it is very simple, nothing to worry about at all. We will just talk about that through. Oh, I deleted that, right? Oh, I should have just created a new one. All right. I can just write it again. So, suppose I have a wave like this. So, what does this wave have, like what are the characteristics of the wave? Remember, this is 0 0. So, it will have some height, the maximum height that the wave can go to, that is referred to as amplitude. Okay. So, from 0, maximum height it can go is plus a, maximum bottom it can go is minus a, alright. Now, there is something else. If you are going to be considering multiple waves together, then suppose you are having another thing like this. So, this is still A. Sorry. This is still A. This is still minus A. But then you will notice there is a shift, where in this wave it is starting at 0, in this wave it is starting at A. So, this shift along the entire wavelength is referred to as phase. Okay. So, this is called phase, and the real part and the imaginary part of microwave is just for you all to represent amplitude and phase. So, is this clear? Shall I move from this? Shall I go back to the slides? Everyone understood amplitude and phase? Yeah? phase, right. So uh, okay, so generally when we see the cycle of a wave, then we divide it into two parts. One is the crest, the upper part, and the other is the lower part, which is a trough. So a standard wave as we know it starts from 0, goes to the maximum, comes back to 0, goes to the minimum, and then comes back to 0. So in the crest we have 0 maximum 0. In the trough we have 0 minimum 0. So I am further dividing this into 0, half, 1, 1.5, 2. Okay. So this half, 1, 1.5, 2, I have just randomly given numbers. Like that, generally we can assign some value to whichever location it is. Okay. So whichever part of this is there, we can assign some number, right? So considering this is half, this is 1. So somewhere in between will be 3/4. Correct? Like that. So every single point is assigned some number. Now,
We can show by angle, we can understand better.
using that,
90-degree angle and 180 degree.
right?
So that
Yeah, I wanted to.
0-degree angle, the peak is 90 degree, and that again the 0 is 180.
Are you going to explain it with a circle?
No.
Then?
Just the straight line, now.
Okay, right.
Reason. You can specify the angles there.
Yeah, okay, cool. So 0, and instead of half, exactly as said earlier, instead of half and 1, I am just referring to this as 180, 360. Okay, so half will be 90 and this will be 270, correct? So like that, some number is assigned to every point. Every single point over here is going to be having some number, correct? So which point, whether the wave is starting at this point or whether the wave is starting at this point, the wave remains the same. It's just the starting point that is varying. So that starting point is the number associated with that starting point, that is the phase. Okay. So in this case the phase is 90, correct?
Both of the waves are 90-degree out of phase. So upper wave is sine wave and below wave is cos wave.
Yeah, that's one. Yeah, you all understood? I'll explain once more. Once more I'll explain this, okay? So, no, all waves have a phase. This has a phase of 0 because it's starting at 0 point. This is considered a normal wave, okay? A normal wave is starting with 0 phase and it has some amplitude A. This also has amplitude A, but compared to a normal wave, it is starting at this point. So that is why this distance, it's starting from here, right? So that is why this is associated with the value 90. So that's why the phase for this wave is 90. Okay? Clear for everybody? Normal wave, wherever it is starting from, suppose I have another one and it's starting from somewhere over here, it's starting from the bottom, then what will the phase be? Huh? Guess? I am drawing two waves here. What is the face of this? What is the face of this? Take a look at this and tell me. This is a normal wave. Based on that, tell me what the phase of those two are. Think again. Everyone saying it's starting from 0, but then take a look at this. Look at the trough and the crest. trough and the crest is important. Someone is saying 90 for this. This. Think again. 90 starting from here. So, whatever number you all are saying, imagine this wave starting from that number. So, does this look like that? Or does this look like that? Right? Yeah, this is 180, 270. Yeah. Yeah. So, over here what's happening? This is 180 and the other one is 270. Okay? Understood phase, right? Fine. So, now let's consider another case. What is the phase of this blue one? It's approximately treat it as touching this, huh? This is as best as I can draw. What is the phase of this? Phase is only going to be the shape of it, not the size of it. Over here the amplitude has changed. The amplitude is the distance from this x-axis till the lowest point or to the highest point. So, the phase is the same. What is the phase over here? 180, right? But the amplitude has become larger. Okay? Is this related to the wavelength? Wavelength is not changing. Everything is the same wavelength. Okay? So, wavelength is not changing over here at all. Fine? So, generally when the data is stored, right, when the data is stored, they store as real and imaginary. So, the amplitude times cos theta becomes the real, amplitude times sin theta becomes, sorry, this is the phase, huh? Not theta, phi. Amplitude times cos phi. Did you all learn cos and sin? Remember? Few of you all? Okay, if you all haven't remembered, don't worry at all. Absolutely don't worry about it. It's just R and I can be related to amplitude and phase with some formula, okay? And that is, that's all there is. Now, you can, if the way the data is stored is going to be having real and imaginary, that's how we are getting the data from the sensor. Now, real square plus imaginary square, the whole square root will give you the amplitude, that's the formula I am telling, and the phase can be obtained by this, okay. These are the two mathematical formula by which you can obtain amplitude and phase. Don't worry about it, you won't be asked this formula anywhere, just think of it as from the data we can get the amplitude and phase from this relationship, okay. Now you all have understood amplitude and phase and the data has come to amplitude and phase, then we will be able to work with the data, okay. Now, yeah, so now we have to come to what is the scatter itself. We saw that the energy is coming onto the surface is going to be scattering it back, right. Now, the scattering is going to be represented by something called sigma naught. So, sigma naught is a backscatter coefficient. This backscatter coefficient is telling you for any area, for an area at a distance of r from the sensor, how much energy is going to be scattered back, and that is going to be energy scattered divided by energy received. Does this look like something similar to what we had in reflectance? Reflected energy divided by incident energy, right? So that way only it's scattered energy divided by incident energy, and then this is to tell you about the distance to the sensor. How much is there based on that, because the sensor is going to be sending out power in all directions. So, and for how far it goes, the power is going to be reducing further, right? So, because of that, we are going to be multiplying by this factor also. So, we will be getting that. Now, these values are generally, very small values, or so for us to make sense of it, or to bring it into a very comparative scale, that's why we refer to this in the log scale. Okay. So, you'll have learned about logarithms in your school, right? So, you're applying 10 log of this is going to be the final coefficient of scattering that we are using. This is called the normalized coefficient of scattering. Okay. This is just the exact same thing as sigma naught, but we are representing it in log scale. Now, let us see how the radar is going to be working. Any doubts so far? You all have you all don't have to understand the formulae and everything of that sort. It might be a little bit too complicated. Don't worry about that. Have you understood amplitude? Have you understood phase? Yes, you have understood different wavelengths and how larger wavelengths, because it's similar to the size of the target, it's going to be scattered and not reflected. You all have understood this? Fine. You all have understood radar principle, where it is going to be incident, like the time for it to reach the target and back is going to be used to compute the distance to the target. Have you all understood that? Yeah, should I explain once more? I'll explain once more. Okay. Yeah. So, this is your sensor, and it is going to be sending the signal, and it is going to be receiving the signal from the target. So, this distance is L, this return distance is also L. Now, it is sending at some time t1, it reaches here at time t1 plus something, whatever, and then it is sent back also, and then we get it at t2, correct. So, we know only sending and receiving ka time. Sending time is t1, receiving time is t2. The time difference between these two is t2 minus t1. The length the distance travelled is L in this direction, and then L in this direction, plus L, which is 2L is the distance travelled. So, speed is equal to distance by time difference, which is equal to 2L by T2 minus T1. Okay. We know C, we know T1 and T2. So, then from that we can get L as C into T2 minus T1 divided by 2. Okay. So, this is how we are getting the distance of an object considering the speed of light and the time difference. Clear? Anyone? Any doubts? Anyone? It's fine? Okay. Now we've talked about radar. When we are working on a space-based or an airplane-based remote sensing with radar, then it is always going to be looking to the side, because we have seen that time distance will give us time distance and speed of light will give us the distance, right? But if it's looking on both sides, then we won't really know if time distance is the only thing we are measuring. It can be either this side or this side, correct? Right? So if the satellite is just moving and looking downwards like this, then what happens? Even if it's coming from this side or this side, the time difference will be the same. No? Should I? This is our radar. It is sending the signal, receiving the signal, everywhere. It is receiving throughout. In an entire beam, it is going to be sending and receiving. Okay. So there might be a point on both sides of the radar where it is at the same distance, or it might be at the same distance. So because it's at the same distance, the time gap will be the same, the time for return will be the same, correct? So what did we see earlier? We saw that if we don't know the distance, we are calculating the distance by c into t2 minus t1 divided by 2. The radar is only calculating t2 and t1. C is known to us, 2 is a constant. So then what happens? T2 and T1 can be the same in this direction and this direction. So we won't really know whether the length is in this side or this side, right? So that can lead to confusion. So because of that, when we are using the radar on a satellite or an airplane, we do only in one direction. We don't do in both directions. Okay. So in one direction if you do, then each of them will be returning at the unique time periods. From that we will be able to get the information. Okay, fine. So this side looking aperture radar, that is called as SLAR, and that was the earlier form of radar remote sensing. Now this is very useful to understand the idea of radar. So we'll get started with this, then I'll show you how it is different from what we are using today, which is called synthetic aperture radar. Okay. So there's only one very small difference between side looking aperture radar and synthetic aperture radar. This is side looking aperture radar because they started doing that sideways they are seeing, so that we will be able to not get that confusion in the location due to the time. Fine. So you'll need to know a few terms. This is just understanding what are the basic terms. If the radar is flying in this direction and it's looking in this direction, the direction towards that side, that is called range. The direction of flight of the radar is called azimuth. Okay. So range and azimuth. Fine. So will you all get confused if I say range and azimuth now? Range is away from the direction of flight, azimuth is in the direction of the flight. Okay. Sideways is range, forward is azimuth. Now when the radar is looking onto the ground in the sideways direction, there is going to be, like, suppose there is a beam of the light which is going to be sent towards the surface, and from there only we will be receiving it, right. So the beam of light is going onto the surface, it touches the surface, one part is closer to the sensor, other part is further away, right. The closer one, that is referred to as near range, because the range, in the range direction it is closer to us. The one that is further is called far range. Understood? Is this fine? Is this okay? Clear? Should I explain again? Yeah. So we have our sensor. Forget about azimuth direction right now. It is going to be putting a beam of light onto the surface. Okay. Now this direction is called range. All right. Now this is closer to the satellite. This is far. So this is called far range. This is called near range. Okay. Understood now? Anyone has any doubts? Now this is called the range direction. Along the center, this is called the slant range. Okay. So this line is called the slant range. It's called the slant range because this straight line is the range. This is the height of the aircraft or this spacecraft. This is the slanting line, right? Slanting line towards the range direction. So slant range. So recall again, you're having a satellite. In the direction of the satellite path, what is it called? Azimuth, right? In away from the direction towards the side viewing angle, that is called the range, right? So that is this. Now this slanting direction towards the ground, that side, that is the slant range. So the distance between the slant, the near range and the far range, that is going to be the size of your image. So that size of the image is called the swath. Remember, you all have learned swath for remote sensing regular. The entire set of pixels that is there for one line, the entire width of an image, that is referred to as swath. Same thing over here, from near range to far range, that is the width of the image. Okay. So that is called swath. Now there's one more thing you need to know, and that is right. So I think I can explain that from this. So this angle over here, this is called look angle. All right. Oh, sorry, I think I placed this slide a little wrong. Anyway, I'll come back to that. So yeah, so along the slant range, the resolution, remember we have learnt resolution in optical remote sensing, reflectance based remote sensing. You all have learnt the resolution. No? You all were telling that 10 meter is better than 100 meter per pixel resolution. All of that you all told me, right? So over there, what happens in along the image and across the image, the resolution remains the same. In case of microwave, that's not the case. Along the range, there is one resolution, and along the azimuth, there is another resolution. So the range resolution can be given right. Let's not worry about this slide. Let's go to the next slide. So okay, fine. the range resolution is given by this direction's resolution. Okay. So, for that it is given by this particular formula which depends upon this cos theta, and then so it depends upon the speed of light and then the pulse width, sorry, the pulse interval which is given by tau, and then the angle cos theta. But in case of azimuth resolution, it has a dependence not only on the theta or the look angle, and it also depends upon the length of the antenna and the wavelength. Lambda is a wavelength. Okay. So, those which are having long antennas, L is the length of the antenna, those which are having long antennas will have small value of the resolution. Big in the denominator means smaller value of the azimuth resolution. So, if we have a very large L, we will have a good value of azimuth resolution. So, this is where side looking aperture radar and synthetic aperture radar is going to be different. Side looking aperture radar has a fixed antenna length. Synthetic aperture radar tries to improve the length of the antenna by increasing the looking at the same location. So, basically there is the flight of the thing, it is looking at one location here, as it moves it continues looking over there, as it moves it continues looking over there. So, effective length of the antenna is from here till the last point, it is not only the fixed length of the antenna, right. So, that fixed length of the antenna will be much smaller than the effective length of the antenna. So, because of that, with synthetic aperture radar we are able to get good values of azimuth resolution. Okay. Fine, clear for everyone? So, this is what is mentioned. Okay. So, the effective length is going to be as per multiple looks. So, the complete length appears to be much bigger than the individual lengths. So, if you were considering individual length, the azimuth resolution can be very poor. So, using this effective length which synthetic aperture radar gives us, through that we are able to get resolutions in the range of 10 to 20 to 30 meters. So, then we are able to get understand a good idea about the target surface. Okay. Is this too much? Are you all having a difficult time? You all have any doubts so far? We can address them now. Yeah, okay. We'll take a 5-minute break and then we can reconvene. Yeah. So, pulse width is basically about the beam that is sent, right? The beam that is sent by the transmitter, it is going to be reaching the surface. Now, that beam is in the form of again a pulse. A number of pulses are sent at once. So, from that how much, what is the period over which that pulse is going to be active, and then there is going to be the negative phase, and then there is going to be the positive phase and the negative phase. So, that width is the pulse width. So, that is going to be helping us understand when the scatter back comes, backscatter comes, right, whether it is coming from this or from another one. Yeah. Anyone else? Okay, so what have you all understood so far? Anyone? One of you guys can tell what you all have understood so far? Tell. Who will save your friends? Yeah. Start from here. Tell me something you understood. Next person can tell me something else. So, if you start first, then you will get an easier thing. Start.
वहाँ तक जाते जाते बहुत कुछ बोलना पड़ जाएगा ना, तो आप स्टार्ट कीजिए.
Side looking the picture.
Mhm.
Side looking the picture. Radar.
Okay,
SLR.
you've learnt about SLAR. Fine.
About the range.
Yeah.
That is, the range is away from the sideline of the flight.
Okay, fine. What about you? Mm-hmm.
Through this azimuth resolution, we have learned the this forward range of flight.
Yeah.
Then it is the ability to distinguish the two targets.
Mm-hmm.
Yes, and it also depends upon the beam of the beam width and the slant range.
Okay, fine. What about you?
About the about the radar, working of radar,
Okay.
and which mean the sideway
Mhm.
means range,
Mhm.
and the forward ways are remote,
Is
azimuth,
yeah.
and then all the slant way and near way far range, that's been I just thrown it in the copy that near range is
Yeah, no worries. Between the near range and the far range, that distance is called SWOT.
yeah. So
Yeah. All right. Next person.
I looking this on the sites, looking the picture rather. And this one, I understand only there's a sensor near that reflects that up and down that this maybe a range up and down near the far.
No, don't worry. Don't worry. You just think and tell. You're fine. You're on the right track. Don't worry about it. Just tell. It's okay. Don't worry. Don't worry. Try. No pressure at all. Just try to tell what you have understood. I'll correct you. Okay, fine. All right. What about you?
I have learned about the range.
Mm-hmm.
That range is far away from the direction,
Mm-hmm.
and azimuth is going on the one direction,
Okay.
and
The flight direction. huh?
yeah, and in the sensor there is a near and far. That in that between,
All right.
yeah, that is called as
Slant range.
Yeah.
Right. So then it's not the sensor which is having near and far. As the beam is falling onto the ground,
Yes,
one part of the beam is near to us, one part of the beam is far.
far.
So the part near to us, that is called near range.
Yeah.
The one far from us is called far
Far
range.
range.
And that diagonal distance is
Yeah.
called slant range.
Slant range.
Okay.
Thank you.
Yeah.
They can explain.
Ah, right. Yeah. Yeah. Yeah, sure. Yeah, she's just asking to explain azimuth resolution again.
Ask them
Ah,
first.
right.
They know,
Okay,
they can
okay.
explain.
Yeah. Anyone is aware? Anyone will be able to explain? Yeah, okay, I'll tell you. Yeah, from azimuth resolution, we'll talk about synthetic aperture. Okay.
क्लिक किया हो गया, ऐसा नहीं होता है। लाल पीला हरा देखने का आदत हो गया सबको, लाल पीला हरा मैप देख लिया, हो गया वही है। कौन था?
Okay. So you can think of azimuth resolution. Forget about this part over here. All the cos theta and everything might sound scary. Let's just look over here. Slant range we learned is the side distance, right? The diagonal distance, correct? So azimuth resolution is given by the wavelength, which is also fixed for any sensor. The wavelength is fixed. The slant range is going to be dependent upon the height and the range which we are going to be considering, right? So forget about, I mean, the look angle, that is also fixed. The only thing that varies is the length of the antenna. So slant range into the wavelength divided by the 2 times the length of the antenna is going to be what azimuth resolution is. Okay. So this length of the antenna, this lambda by 2L, I mean lambda by L, that is coming from the beam width. No need to worry about that. This L is the length of the antenna. Okay. So this is going to be the direction of the azimuth. Now suppose you are having, say, a slant range of how many kilometers will be there? 800 kilometers, 1000 kilometers, or it can be even higher. And then something, maybe even if you put it as 10 to the power 4 kilometers, lambda will be in the range of 10 to the power minus 2 or so, right, because it's the wavelength associated with it. So for having a good range resolution, we'll need a huge antenna. A huge antenna is required for transmitting with that much power and receiving with that much power. So for that, I mean receiving with a even lesser power. So for such a huge antenna, it's going to be difficult to take it to space and put it over there, right? It's really going to be difficult. So for us, it will we need a very large aperture size to get good azimuth resolution. Okay. So the main thing which matters in azimuth resolution is the length of the antenna. Fine. In case of side looking aperture radar, they try to keep as big antennas as they can, as we can possibly get, but then that is not always feasible. That is not always feasible because such huge cumbersome things cannot be taken into aircraft or cannot be taken into space. So what is the next step? We need to try to set up a larger antenna through an artificial way, and that is done through synthetic aperture radar. So what happens is, the radar is looking at one location, and then even as the radar moves forward, instead of looking at the next location, it continues looking at this, and then as it moves to the next location, it continues looking at this. So because of that, the effective length of the antenna will be equivalent to the complete motion of the antenna of the radar itself. So this effective length of the antenna will become very large. Because of that, azimuth resolution will become small and good. Okay. So that's how we are able to have a synthetic aperture radar, because the length L is not originally there. We are generating it by looking over that particular location multiple times, no. So that generated thing, it's synthetically generated. Synthetically means we synthesizing the longer antenna. So that's why it's called synthetic aperture radar. Okay. So this is what we are saying. Suppose this is the target. From this location it is looking at the target. Next time also it's looking at this target. Next time also it's looking at this target, and so on till it reaches here, it's looking at the target. So this entire thing becomes the effective length of the antenna. So that's why it is much larger than what is originally the antenna size. Fine? Clear? So instead of this L, it will be effective length, this big L. So when this value is very big, this value will become small, and so we will have a good resolution. Hmm? Yeah, can. It's a good place to stop, I guess, for now. We'll have a small tea break, process, we'll come back.
नितिन जी वो बोलिएगा चाय लगा देगा बन गया था पूछिए किसी को कुछ पूछना है तो
Yeah, ask if you have any. Not longer range, longer antenna, better resolution.
सबका चेहरा देख रहा है कह रहा मैं बोल क्या रहा है सबका चेहरा देख रहा हूँ सब कुछ दिमाग लगा के बैठा
Yeah.
रेड वाला देखा सीरियस क्वेश्चन कुछ नहीं
Yeah.
एक घंटा और चला गया इनके नाम पूछे थे वो भी
देखो तो ऐसा क्यों है पता है तुम लोग क्वेश्चन कर ही नहीं रहे हो कुछ पूछोगे तभी समझोगे
True.
नहीं तो ये तो फिर वहाँ से ऑनलाइन भी दे देती हैं फिर इनका आने का क्या मतलब है पूछोगे तभी जानोगे क्वेश्चन पूछ ही नहीं रहे हो कोई नहीं और ये वाला पता नहीं इसको मिक्स करूंगा मैं उधर ले जाऊंगा मंडे से
Yeah, yeah.
All these people, they don't have
No,
any
from near range to far range. Yeah, should I draw? So your thing is here and your beam is here. This is the ground. So this is near range, this is far range. This is the image width. Image width. Near range to far range is swath. It's the same as image width. Yeah. Oh, far to near also same thing only. It's just the distance.
Okay, it's
Yeah.
just the distance.
Yeah. Advantage is that this radar is active, so then it is giving the light and receiving the light. So because it's giving the light, even at night time it can operate. We don't have to depend on the sun. So day and night capability is there. Second one is weather. Yeah, it's an active sensor. Yeah. Then second one is that during rainfall also it does not modify in the atmosphere. Like generally when we are looking at visible or infrared light, it is going to be sent back in the atmosphere. It's going to be absorbed or it's going to be reflected or something is going to happen. In passive sensor, it will be active. It will work only during the daytime because sun is the source of light. Yeah. So then so because of if there's rainfall or cloud or anything, then in case of microwave it will go through, no problem. Okay, yeah, that's the advantage. Yeah. Any others? Any doubts? Do you have any doubts? Okay.
we can have discussion.
Do you guys have any doubts? Okay. Sure. Point sensor, and then you're looking at the surface, and then the sensor has to move from left to right, and also next line, and also next line. That is called whisk because it moves from side to side.
सफाई वाला झाड़ू लगाता है
Yeah,
देखो
exactly, exactly.
हम लोगों को जो समझाया गया था मास्टर में, वॉशरूम के धक्का देते जाओ, आगे
Yeah,
जाएगा।
yeah,
वॉशरूम पीने के बाद जो होता है, जो विस्की लेने के बाद लोग ऐसे ऐसे घूमते हैं, ये हमें बस एग्जांपल
I
दिया।
think you're still on
हाँ,
live. You're
no
still
problem.
live.
But these are the common use
Yeah, yeah.
example we can give the student.
Yeah, yeah.
They can understand better.
That is whisk room only.
Just for formality, you will do, no, when mom asks us.
So पीने के बाद देखो लोग कैसे चलते हैं, टेढ़ा मेढ़ा, वही हो गया। From whiskey it comes to whisk.
Yeah, any other doubts? What about you? Any doubts? Okay. Alright, then I guess we can have tea and then come back to you guys.
चलो चाय पीते हैं।
Huh?
पागल हो जाएंगे। नहीं पियोगे चाय? Hello, hello.
For microwave data, the data that we get depends not just on the target. So in case of optical, what did we see? In case of optical, multispectral and hyperspectral data, we saw that the target properties is going to be giving you the spectrum. There might be modifications because of the atmosphere, but then the data will always be representative of the target, correct? What happens in case of microwave? It's not just the target, but also the radar parameters that can make the data look very different, okay? So, there is something called polarization, which we will talk about shortly, and then the wavelength. We talked about wavelength, right? We saw bigger wavelength, wider wavelengths, and smaller wavelengths. We saw how it is appearing, transmission through the atmosphere, remember? Just 1 hour ago we saw that, right? So, and that's why we are able to pass through the clouds and see during the rain time also. That's what we have seen about the wavelength. So the wavelength of the radar matters, the polarization which I will talk about, and the angle in which the radar is viewing the surface. That is also going to matter. Okay. So based on all of these three things, the data is going to be appearing differently, and also there are target parameters. So majorly is the surface roughness. So the roughness of it is going to be affecting the scatter. The scatter is going to be affected by the roughness, and finally there is something called the dielectric constant. So dielectric constant is a property of the material which tells us about how well, I think if I tell you from the physics perspective, it will be a little confusing for you. So let's just say that different materials have different dielectric constants, and for each of those dielectric constants, the value is the value of the dielectric constant is going to affect how the return, the scatter back is going to look like. Okay. So for radar data, the factors which are affecting it from the radar, the wavelength we mentioned, right? So for optical, we saw that if we are having a forest, we see the top of the canopy. To get the structural information, we need longer wavelengths. So what happens in case of X band, which is 3 centimeter wavelength? We can see the upper parts of the initial parts of the structure of the canopy. If we go for slightly longer wavelength, which is C band, we can get some more structures like the branch structures, etc. Then if we go for L band, we can get the entire structure of the trees. If you want to do a modeling of the tree, the volume and the total carbon that is there in the tree, all of those sort of models can be done with L band data. P band data will be able to go all the way to the surface, and from that we can also get what are the soil characteristics of that area. All of this can be obtained for various wavelengths. Okay. So generally a radar is specifying a particular wavelength range it's operating in. It can be either X band or C band or L band or P band. So we need to choose the radar based on what our application is. If our application is to study the soil moisture, and if we take an X band radar, we are not going to get any information. So for that we need to choose a P band radar. Okay. Is this clear? Fine. Take a look at this. Both of these are radar images, but this is L band, I guess, and then this is a lower C band or X band radar. You can see there is one faint line over here. Can you see this line over here? Not there over here? You don't see anything over here? That's because of a tornado scar. Okay, so we are able to see the modification in the structure of that location, and because of a tornado after passing through, because of this P band radar. All right. Now, so the target properties which are going to affect is, as we mentioned, the surface roughness and the dielectric, right? So based on the surface roughness, there is going to be a lot of different backscattering. So in case of a rough surface, there is going to be a backscatter unevenly in all directions. In case of this tree-like structure, there is going to be volume scattering. So for within the branches and everything, the light goes in, and then it's going to be spread amongst itself, and a part of it is going to go out. But what happens over here and over here? It hits the surface, it gets sent in this direction, and then it is going to be sent back in this direction. So this is called double bounce. The first bounce over here, second bounce over here. Double bounce, it generally has a very high backscatter value. Okay. So generally if you see a very high patch in microwave data, that is indicating that there is fewer of the branches and leaves and all of that, and more of the tree stumps, or it can indicate a urban area. In case of water, it appears dark, because in case of water, surface is nearly flat, and then it's going to be reflecting the energy away completely on the other side. So then there's nothing coming back towards the microwave sensor. Okay. So because of that, it appears dark. Fine? Is this clear? So water appears dark. Those bright patches are indicative of double bounce, which is near urban areas like large buildings or the stumps of trees. And then these are kind of lower lower values of backscatter. So next is about the target itself. So for different targets, for example, in case of sand, loam, and clay, these are different categories of the mud itself, right? So they will be having different textures. So based on that, how much can a radar penetrate? So those radar which are having very like based on the soil moisture, the dielectric constant is going to be modified. So based on the soil moisture, the dielectric is changing, and as a result of that, how much it's able to penetrate is going to be reducing. Those with very less dielectric, I mean those with very less soil moisture, it's going to be not. It is going to be sending it off from. I'm sorry. What have I written here? Yeah. So the skin depth is going to be very high because it can go further deep inside in dry soil. But in case of those with a very high soil moisture, it's not going to be able to penetrate much. It's going to be only penetrating up to a few, like a few centimeters. So a few centimeters it will be able to go for different radar ranges. So you can see that the smaller frequency, larger wavelengths will be able to penetrate to larger extent, right? So that is the case. Now see this example here. This yeah, so what you see over here, this patch is where the radar image is able to look into the into the depths. So into the depths of the soil, it appears to be sandy soil, and then because the radar can penetrate into the sandy soil, they have imaged that there used to be in this depths of the Sahara Desert, there used to be some river patterns that used to exist in the past. So that is going to be very useful. So you were mentioning that you were working on archaeology, right? So this is also going to be used in archaeology because in certain areas where things have been, buried under the surface. So if the soil moisture is not too high, then the radar will be able to penetrate to a good extent. We will be able to understand the subsurface features as well. Okay. See over here for absolutely low soil moisture and for a very low frequency system, radar, we'll be able to get up to around 50 to 100 meters of depth also. Up to that much we can go down. Okay. Yeah. Yeah. So. Yeah, so what's happening here is this is an image of Sahara Desert. Looks like bare sand, right? Once we take a radar observation of it, we saw that there are a lot of patches which appears to have some water systems. So it is not that these water systems are existing today. Long time ago it used to exist and now it is covered by sand. So this radar is able to penetrate the sand and see what is submerged under all of those meters of sand. So that is what is represented over here. So for seeing below the surface beyond what we can see, that also is going to be provided by radar. There is one condition, soil moisture should be low. You can see over here, as the soil moisture is increasing, that less a depth it can go down to. So one soil moisture increases to maybe 0.2 grams per centimeter cube. Then for a regular radar, it is only going to be going up to 1 centimeter depth, 10 centimeters depth, around that range. Otherwise, it can go even up to 10s to 50 meter depth. Which one? The graph? The photo was taken at the same time. This is also a part of that regular infrared view itself. All of this is infrared. Only this patch is microwave. This patch in infrared, this patch in microwave. Okay? Same time, similar time. Yeah. Yeah. This was, I don't remember the name of the sensor. I think it would be Sentinel only, or ERS. ERS or Sentinel, one of these two will be used. This specific one, huh? This one mostly will be Aster probably, I don't know. Okay.
You know,
Yeah.
please explain the graph, man. I
This graph?
understand why is 100
Yeah.
this red line. It's
Okay. Sorry? This one? Yeah, probably Sentinel-1 or ERS, one of these two satellites. So these are, we'll talk about those satellites once more before we stop, okay? Yeah, yeah. Yeah, I'll get to you in a minute. Oh, right, okay, fine. Okay, so I think that's essentially what both of you all are trying to ask, right? So this talks about how much of the soil it can penetrate. This the sensor, the microwave will be able to penetrate and give us information of. Okay, so we are getting, for sandy soil, we are getting the highest up to around 100-meter depth. We are able to go down and see whatever is there for this frequency range. For higher frequency ranges, for sandy soil it's going on, like for sandy soil it goes only till 0.1, okay, for higher frequencies. So that is shorter wavelengths. So for long wavelengths, we can say that we get very good penetration for sandy soil. Even for loam and for clay, we are getting decent amounts. But then if you see the soil moisture, right? So for very dry soil, we are getting very high penetration. For very moist one, it is having lower, okay? It is not going into sufficient depth. So suppose what we are trying to say is that suppose you have some object which is under sand at 50 meters. Now if the sand is dry, then we will be able to see very easily using this sensor. You won't be able to see at this sensor or this sensor, but then you will be able to see with this sensor. But suppose the sand is wet, then you won't be able to see at all, okay? Yeah. It's okay, don't worry, ask. Yeah. All right, so always the lower frequency or the higher wavelengths is going to be giving you better, the depth of the, better penetration depth. But then the problem is that even if we are going with that for more moist soil, even if we are going for that, if the depth is more than 1 meter, we are not going to be getting any information. So for such situations, generally we go for this like on the ground surveys are there of ground penetrating radars, but then that one also will have limitations in case of very moist soil. Okay, yeah. Any other doubts? Yeah. Yeah. Yeah.
It goes only till 10 to 15 centimeters.
Right.
What about the hilly region?
Oh, in hilly region there is okay, that's actually quite an excellent question. So in hilly areas, microwave data requires a lot more processing, terrain correction needs to be done. So that one, it becomes a bit of an issue. The major properties are again going to be soil moisture and the surface roughness and everything. But then when you are looking at a hilly region, there might be the size of the image might appear shorter or longer in certain cases. So because of that, we might miss some information. So that's where it becomes challenging. But otherwise, it's going to be mainly dependent upon the moisture and the target property. Yeah, because the material itself will be a little bit distorted when we're looking in hilly areas. So the correction for that is a little bit involved. Yeah. Yeah. Any others? Anyone? Okay, let's go. Yeah, so now it comes to polarization. So polarization also affects the way that we are going to be having how we are able to view the targets. Okay, so polarization can be imagined this way. So suppose we talked about the wavelength, right? We talked about the wavelength, we drew all of those lines and we talked about the wavelength. Now light, when we say has a wavelength, it's because we call it the electromagnetic spectrum. So light has a wavelength in the electric domain and in the magnetic domain. Okay? So based on the direction of the electric field, whether it is vertical or whether it is horizontal, that is referred to as polarization. So we fix one direction as one is fixed, and then that is always treated as horizontal, and the other is treated exactly 90 degrees is going to be treated as vertical. Okay? So here, this is the vertical plane where the wavelength is like this. In case of horizontal, it will be like this. So the light can either be vertical or horizontal, or maybe different beams of light will be, some will be vertical, some will be horizontal, like that. So if many of them are vertical, many are horizontal, and all other angles also are possible, not just horizontal and vertical, all other angles are also possible. So if all of those are coming, then it is going to be referred to as unpolarized light. Now for polarized light, we are saying that it is either horizontal or vertical. So we have some filters that can be used for polarizing the light. So even in your shades, some of your shades will be coming like the you'll use shades, right? The sunglasses. So those will be polarized, and you might be asked to do a polarization check where you can wear that and you'll see some other mark on a card or something like that, right? So that basically comes because only light with electric field in one direction is allowed to pass. So when you are sending the light from the antenna, you can send it either in horizontal or vertical polarization. And similarly, when you are receiving it, you can receive only horizontal or receive only vertical. Okay? See this over here. This is a light wave. It is going to have electric field, and then if the electric field is like this, then the magnetic field is going to be like this. Okay. So when we are showing both the electric field and the magnetic field, the entire thing looks a little confusing. So we just show the electric field and it is understood that magnetic field is going to be in the other direction. Okay. So electric field is seen over here, and if the electric field is like this, magnetic field is like this. If the electric field is like this, magnetic field is like this. Okay, fine. Now if the electric field is like this, it's called horizontally polarized. If it is like this, it is vertically polarized. Okay. Now suppose we have, sorry, suppose we have the transmitter transmitting in horizontal, then it is coming back and receiving in horizontal. Horizontally polarized light is sent by the transmitter and horizontally polarized light is received by the transmitter. So this is called H. Similarly, if vertical is sent and vertical is received, that is called V. Then if horizontal is sent and vertical is received, H V, and finally if vertical is sent and horizontal is received, VH. Okay. So the first is what is transmitted. Horizontally polarized is transmitted, and the second is what is received. So here horizontal is received. Okay, fine. Explain again. Okay, I'll explain what polarization is again. Only this part, right? Okay, fine. So you have understood about polarization, and you know that the radar is going to be sending light and receiving light. So sending is called transmission, receiving is receiving anyway. So when it is sending the light, if the electric field is in the horizontal direction, that is called horizontal polarization, sending. While receiving it, if we receive only those horizontally polarized light, that is received horizontal. Okay. So suppose we are sending horizontal and receiving horizontal, it's called HH. If you are sending vertical, receiving vertical, VV. H for horizontal, V for vertical. Okay. So the first one is what we are sending, second one is what we are receiving. So what's happening over here? Horizontal is sent, vertical is received. Okay. Now finally what's happening here? Vertical is sent, horizontal is received. Okay. So these are the 4 different polarizations that are there, and all of them look a little bit different when we are visualizing the microwave data. I'll show you how that looks. Yeah. Yeah, so that is generally like we use that Polaroid to make sure we are sending only in this, and the received one also we use that polarizing filter. So then we'll be getting only from that right now. So if it is unpolarized, then we won't be able to get the full information. Like there'll be a lot of noise in the data. So that's why we prefer to apply a polarizing filter before we send it, and then we take, while taking also we apply a polarizing filter. We receive and send, that is as per the sensor design. Yeah. Alright, so when you're downloading that, then most of the time we download I'll explain about that also. So most of the sensors, they will have if they have both vertical, if they have all 4 modes, then it is referred to as quad pole. Okay. Now if they have only two of these, then it's called dual pole. So most of the sensors available for free we might get on dual pole mode. Quad pole is mostly paid. So that's how it is. Some sample data is available for us to try out with, but then unless in case of an emergency disaster or something of that sort, we don't really get access to it. Is this part clear to everyone? Understood? So let's see how the different polarizations look. So you can see that HH is appearing over here and VV is appearing over here. Okay. So there might be a few things which might not be visible in HH which is visible in VV, and vice versa. So generally we saw earlier about this double bounce, volume, rough surface, all of that, right? So then some of these polarizations are more prominent in VV, some of these are more prominent in HH, and some in HV. So that's what we would be expecting. Okay. So that's this is the false color composite which is made by combining all 3 of them. Yeah. So so this is some of the resources you can use. Both of these, they have a number of tutorials on their website. So if you want to take up SAR data and do the processing of SAR data, then those 2 are what you should be using. Then yeah, anyway we are sharing this with you, so you all can access it. Yeah. 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 Yeah, so earlier we used to use different wavelengths. Here we are using different polarizations, because for each polarization mode we get one image. Vertical send, vertical receive one image, vertical send, horizontal receive one image, horizontal send, horizontal receive one image. So those three can be combined to create a false color composite. It's not exactly like our false color composite, because our interpretation, the interpretation in SAR will be different. Okay, so you can't really say that the red areas are vegetation or anything of that sort. So I'm just trying to show you that these three can also be combined to create a false color composite. And this false color composite we should be interpreting from whether HH is going to be giving what type of scattering. Is it going to be volume scattering, double bound scattering, like that we should be interpreting. Okay. And finally, I want to circle back. So based on the value of the backscatter coefficient also, we will be able to like understand a bit about the different objects. Okay. So for lower backscatter, it's generally for smooth surfaces like water, lakes. We saw that it was all black, right? Those areas are black. Then even in case of roads which are very smooth, so in case it's very smooth, then the wavelength is not going to be in the same range as the surface roughness. So we are not really going to be getting much of a backscatter value there. So if we are having a very high roughness and the wavelength is in similar ranges, then it's going to be scattering very high. Okay, so that will be very prominently there in case of this dense vegetation and others, even agricultural areas. But where we will get the most is when there is double bounce, because it's almost like it's reflecting back, because it does one bounce and then the other bounce and it goes all towards the sensor itself. So wherever double bounce is there, we'll get very high values. So that's where we see in case of urban areas and very steep slope areas like hilly areas, we'll be getting all of this. Okay. And let's circle back to this then. So now you all have understood that not just the wavelength of the sensor or the target property, sorry, not just the target properties, but the wavelength of the sensor is going to matter. The polarization is going to be mattering, right? So all of these things are going to be mattering. So with this, you can just take a look at the different bands and what the applications would be. So for P band, where wavelength is very large, you can say that it's going to be penetrating to a good level. So even if you have a forest, it can penetrate till the ground and get the soil moisture results, right? In case of L band also, it will be able to give us a good structure of the canopy, etc. But in case of C band and S band, it can be useful for agriculture, right? And then for other aspects, a shorter wavelength will also be used. Fine. These are, yeah. Right. So those FCCs, we will not be able to get a false color composite like how we are interpreting this, because in reflectance based remote sensing, we are understanding what the color signifies to us in the form of the target property. That is not the case over here. We will have to interpret the color not just in terms of you know, red is vegetation or anything of that sort. We will be saying red will be associated with volume scattering. Maybe it can be because of vegetation, or it can be because of some other features also. Like that we'll have to say. It's our understanding is not in terms of the composition, but in terms of the structure. So the way of thinking should change a little bit there. Okay. Yeah, so this is circling back to some SAR satellites. An ISAR mission is going to be coming, it hasn't been launched yet. Available data set right now is Sentinel-1, which is free for use for everyone. Some products of ALOS and TerraSAR, I believe, are available. RISAT is available upon request from Bunidhi. All right. Any other queries? Anyone? Any doubts? Yeah, once more I'll explain. So the antenna is going to be transmitting and it's also going to be receiving. When transmitting, we apply that polarizing filter and then make sure that the energy which is sent by the antenna at that time is only in horizontal. So that means initially many angles of electric field will be there, but only those in horizontal is allowed to pass. So what is falling on the target is only those which are horizontally polarized. After it is going to be scattered back, it will lose that sort of polarization, and among the back scattered value, some will be horizontal, some will be vertical, some other values. So when you're receiving it, you're just going to be picking horizontal again. So when it is coming back, is it largely going to be sent in horizontal? If it is largely going to be sent in horizontal, then majority of the information we are also getting back. If it is going to be sent largely in something else, then if you are applying that horizontal filter, then we won't get much information. So it's like we are sending in horizontal, but while coming back, it's not coming in horizontal, it's coming in something else. So that is what is meant, like that is what how you understand it. Okay. So it sends in horizontal and receives in horizontal is given by HH. Then whatever is there first is what it sends in, whatever is there second is what it receives in. So this is sends in vertical, receives in vertical, sends in horizontal, receives in vertical, sends in vertical, receives in horizontal. Okay? Yeah. All right. Anyone else? Feel free to ask, no problem at all. Horizontal and vertical? Yeah. Yeah. Oh, we generally just refer to them as the HH or VV or HV images. So that is like instead of the band name, right? Like the band or the wavelength. So for a microwave sensor, we generally don't work with multiple wavelengths at once. We generally, like one sensor generally has only one wavelength. So with the exception of certain missions like like NISR, which is coming up, which will have two, but generally they have only one. So bands are not wavelengths here. I mean, bands are wavelengths, but then we are considering only one band, right? So when we are visualizing it in multicolor, that is in terms of polarization. It doesn't have to be only in terms of polarization. It can also be temporal. For example, if you are saying that there's a city and after a particular number of days, there's been an earthquake and then the city was completely demolished, right? So then if there's microwave data that's coming in the city, then it's going to be very high. So then if you are if you're sending, it could be very high in say VV or something. So if you take VV of time 1 as band 1, that is color red, and VV of the same, for another time step after the earthquake as blue, and then VV for another time step as green. So then those areas where the building was there earlier, that is going to be coming as red because we are putting red, green, blue, right? So that sort of visualization or temporal composites can also be created. We don't have to restrict ourselves to wavelength composites. We can do through polarization composites or temporal composites too, but that is just going to be an additional step. So, anyone else? Okay. So I guess then we'll come to a close. That's fine. Then yeah.
Question, ma'am.
Done. Yeah. One question is there.
You said that this wavelength, if we send horizontally,
Yeah.
then it come back horizontally.
No, it can come back. It can come back in anything.
Yes.
But if you apply a filter for making it come back in horizontal, that is called HH.
But suppose for this HY,
Yeah.
suppose it send horizontally, then it come back in vertical.
Huh.
Can we get the image of that?
Right.
How would we do that?
So,
We identify.
oh, whether when you're looking at it, not really. I don't. Oh, sorry. So I can show you an image of it. this is an image of sending horizontally and receiving vertically. So the differences is going to be in terms of some of the properties, like water is going to be always going to be having that sort of a specular reflection. It's going to the other side. It's not going to come back to the sensor, so it will appear black. But then this one is going to be likely in case of volume scattering, when things will change quite a bit. So where there is a lot of forest or something of that sort, we would be expecting a bit of a high value over here. Okay. So it's only where the polarization is expected to change a lot, that's where HV is going to be giving you a high value. Okay. But just by looking at image, we can't really say whether it is going to be HH or HV or VV. That is given to us along with the data set. Huh? So from that we will be able to interpret about the data. Anyone? Anything else to add to this? Okay. Yeah, fine. All right then. Yeah, I think it's been a bit of a session. It's okay. Drop me a message whenever, like drop me an email whenever you all have any doubts. We'll try to sort them out. Okay? Yeah. All right. Sorry? Okay, yeah. So generally we use a software called Snap. I'll also share one tutorial link, so maybe that can be circulated to all as well. So we